This problem is really a beautiful problem because um, after we have done so many problems on measurable sets and their properties, the natural question is everything in R, any subset in R, is measurable? And in the sense of Lebesgue, of course. And the answer to this is false, and it's a little bit tricky. The construction is a little bit tricky, and uses the fundamental idea here is using the uh, translation invariance of the Lebesgue measure, number one, and number two, the fact that the rational set is countable. And then, of course, knowing that the family of all measurable sets is a sigma algebra, sigma being countable here, then this will give us the building blocks for this example of a non-measurable set. Okay, so first, so we are dealing with the set 0, 1, and we're looking at this relation x in relation with y if and only if x minus y is rational. Okay, so this is definitely an equivalence relation. Remark, one may want to define another relation that x minus y is irrational. And this one is not an equivalence relation. And the reason is because the sum of two irrationals may not be irrational. And also if it's not reflexive, if you take x is not in relation with x, since 0 is not irrational. Okay? So the symmetry is there. Okay? In other words, for this new relation, let's call it star. So we do not have x reflexivity. This is not true. We do not have, we do have, sorry, this symmetry for the simple reason that the opposite of an irrational is irrational. But what we don't have is, so this is, but what we don't have is the transitivity. Huh? Okay. Okay, so this may not be true because the sum of two irrationals may not be irrational. So you don't have reflexivity, don't have transitivity, but you do have symmetry. In the case of R, okay, in this case here, then it is true. Why? Because first of all, it is reflexive because 0 is rational, and then symmetry because the opposite of a rational is irrational, and the sum of two rationals is rational. So it is an equivalence relation. Once we establish that R is an equivalence relation, then we can talk about the equivalent, the class of x for every x in 0, 1. Okay, so we can look at the y's such that x is in relation with y. Okay, and what's interesting is that if you take two elements for every x1, x2 in 0, 1, so we know that either, so if this is not empty, if and only if, and it's really amazing, is a property of equivalence classes if they are equal. Okay, so the two are equal. Let me also make another remark that for every x in R now, so because some may ask what happened, why are you focusing on 0, 1? Because in fact the equivalence class for this relation, okay, by extension, because remember for every x in R we know that there exists a unique integer, okay, such that n is less or equal than x less than n plus 1. So our x is going to be n plus x minus n. Okay? And therefore, x minus n belongs to 0, 1. In other words, what we have is, so we can always go back to 0, 1. So we can easily define R on the entire set, of real numbers, but still it boils down to the interval 0, 1 anyway. Okay? So now what we want to do is define a choice function using the axiom of choice. So this will tell me that from 0, 1 into 0, 1. And what I'm doing is I'm taking an element in the class of X. So the axiom of choice allows me to pick one element from the class, the equivalent class of X. And again, what's the fundamental property of this choice function is that if X is in relation with Y, so we know this is true if the class of X equals the class of Y. And then, of course, here what we have is that the choice of X is the same as choice of Y because it's the same class. So we're picking one element from that class. And what happened now if X is not in relation with Y? So in this case, we have no intersection between the two classes. And in this case, phi of X will be different from phi of Y. In fact, we can say even more. We can say that phi of X minus phi of Y is irrational. Okay? So it's not just that they are different, that the difference is an irrational number. Okay. So now what do? We take the set P, which is the range of this choice function. Okay, so this is the set of phi of X for X in 0, 1. And we want to show that set P is non-measurable. Okay? So first of all, what are the properties of P? So let us take assume not. Okay, assume not. In other words, P is measurable. Then in this case we have since P is a subset of 0, 1, okay, so the measure of P will be less or equal than 1. Great. So next, what happened if we take now R in Q and we look at the translation of R plus P? It is measurable, and we know that the measure of R plus P is equal to the measure of P. Okay? Great. So now, knowing that Q is countable, we can consider now R plus P, where R belongs to Q. Okay? Of course, we can consider only the rationals between 0 and 1, so that will not change anything anyway. So we can consider now intersect 0, 1. And we know that this set is measurable. And we have the measure of the union of R plus P, where R is rational between 0 and 1, sorry, is less or equal than sigma of the measure of R plus P and since we are dealing with countable rationals, this will be so this will be equal to sigma of the measure of P, where R belongs to Q, intersect 0, 1. Okay? So what's interesting is this inequality will not give us what we want. Okay? But what's interesting is the fact that we can look at these sets because this may be infinite. That's the idea here. So this here may become infinite, and then this will not help us. But if we notice that for R1, R2, two rationals in 0, 1, then what happened? These two sets, R1 plus P, intersect R2 plus P. Their intersection is empty, provided R1 is different from R2. Okay? And the reason is, if it's not empty, if X belongs to R1 plus P intersects R2 plus P, then X is equal to R1 plus X1, okay, equals to R2 plus X2, and therefore you have X1 minus X2 equals R2 minus R1 is rational. And this is not possible if X1 is different from X2. So this tells you that this is, from what we said earlier, that X1 is equal to X2, okay? And therefore, R1 is equal to R2, which we claimed that's not the case. We took two different rationals, okay? Therefore, these sets are, so which tells me that the measure of the union of R plus P, where R is a rational between 0 and 1, okay, is in fact equal to the sum of R plus P for R in Q 0. Okay? And now we can see that since this set is bounded, it has a finite measure, it can't have an infinite measure. Okay? And this one is equal sigma of the measure of P because of the invariance. So this forces the measure of P to be equal to 0. On the other hand, it's easy to see that 0, 1 is included in the union of R plus P, where R is rational between 0 and 1. Okay? So for every x, it's obvious, for every x which belongs to 0, 1, we have x which is equal to the choice phi of x plus a rational number. Okay? And therefore, x belongs to R plus P. So remember, phi of x is the choice we took from the class of x. Okay? So this tells us what? That the measure of 0, 1, which is equal to 1, is going to be less or equal than, I mean, it's equal, sorry, 0, which is our desired contradiction. Therefore, P is not a measurable set.